This video will demonstrate how to develop a multiple regression model, which includes dummy variables. Displayed here are data about all homes sold in a small town in 1 year. Price will be our dependent variable. Note that the numbers are in thousands, so 263.1 is $263,100. We're going to use multiple regression to develop a regression equation which can be used to predict home prices. We're including two dummy variables, pool and garage, which have only two values, 0 for no and 1 for yes. Let's first check for multicollinearity. Go to Data, Data Analysis, and we'll use the correlation function. I've selected all of the independent variables to be included in the correlation analysis. My data are grouped by columns. I included labels, and I'm going to have the new worksheet on a tab called Correlation. Different textbooks may give different limits. Let's say that if a correlation is between -0.7 and 0.7, then we are not concerned about multicollinearity. Here, none of our independent variables have a strong enough correlation to indicate multicollinearity. Next, let's run the regression. We'll go to Data, Data Analysis, and click on Regression. In our Y range, we will select Price. The input X range will be all of our other variables. I have selected Labels, and I'll have my new worksheet be Regression with 6 variables. Click OK. Right now, this model has an R-square of 0.53, which indicates these 6 independent variables account for 53% of the variation in home price. Do all of our independent variables contribute to the model? Let's check their p-value. The only one which is not significant, the only one which exceeds 0.05 is distance. When we perform backwards elimination in order to determine which variables are significant and should remain in the regression equation, we do it one variable at a time. If we had two variables which had p-values in excess of 0.05, we would select the p-value that was largest and remove that variable first. However, in this case, there is only one to be removed. I'm going to go back to my original data set, and I don't want to lose track of my original data set. I'm going to make a copy of that data set and name it Multiple Regression 5 Variables. And I've kept the copy of my old data. Now that I've removed distance, I can run regression again. In my regression dialog box, it remembers what I had in it last time. Now that we've removed distance, I'll change this to F. Let's change my output to be on regression 5 variables, and because I believe that I've removed the only non-significant variable, I'm going to run residual plots and normal probability plots and click OK. This small change from 53% in R-square to 52% indicates that the variable we removed did not have much effect on the predictive ability of our model, as we expected, given its high p-value. Now let's take a look at the Anova output. All of the remaining variables have a p-value less than 0.05. If anything had changed, we would again remove the variable with the highest p-value and run the model again. But we're done at this point. Let's check our normal probability plot for homoscedasticity, or lack of variation around the trend line for the independent variables. This is our normal probability plot. I'm going to add a trend line. If our variables hug the trend line closely, we have homoscedasticity. And although we see a slight curve, it's actually pretty close to the line until we get to the upper end of home prices, indicating there might be a shift in the predictive power of our model at higher home prices. Now let's take a look at the residual plots. We can use them to check for linearity in our model. We don't need the plots for the dummy variables, which have only 2 values, so I'll go ahead and delete those. The plots for bedrooms and for baths are also not particularly useful because they have a small range of discrete values. However, one thing we see here which is good is residuals both above and below the x-axis. This is the residual plot for size or square footage. We want to see a random plot of points around the x-axis. without a clear pattern. This plot shows decent variation around the x-axis without clear evidence of a pattern. I conclude that we have linearity. Now it's time to put together our final regression equation. Remember that our sales price is in thousands of dollars. What this equation says is, for each bedroom added, we will add $7,169 to the sale price of the home. For each square foot added, we will add $39 to the price of the home, and so on. In this video, I've demonstrated how to build a multiple regression model, how to use backward elimination, check for multicollinearity, homoscedasticity, and linearity. In this video, I'll demonstrate how to conduct a goodness of fit test on nominal scale data to test a hypothesis comparing an observed set of frequencies with an expected frequency distribution. Let's begin with a hypothesis test of equal expected frequencies. This data set is a sample of 150 viewers of 3 different news programs for one particular night. Is the difference in viewership small enough to support the claim that the stations have equal viewership? That's our null hypothesis. Our alternative hypothesis is that there is a preference with respect to TV stations. We will conduct the test using a 5% significance level. This is a goodness of fit test. We'll use the chi-square value to compare the observed frequency with the expected frequency distribution. In this case, we have equal expected frequencies. Our expected values are that 1/3 of the 150 watched each channel, so we'll fill in this column of expected values by multiplying the expected percent times the total, and I'll lock that cell and drag it down the column, and now we're ready to run the chi-square test. Note here in this cell where I'm going to put the output that it says p-value. That is because when we run the chi-square test, it actually will output a p-value rather than the chi-square value. Let's go ahead and do that. Equals chi-square dot test, open parenthesis, and as you can see, it asks only for the actual range and the expected range, close parenthesis. This p-value of 0.007 is compared with our significance level of 5%. It is much smaller. We reject the null hypothesis and conclude that viewership preference is not the same for all channels. The p-value here is the probability of observing this large a difference between the actual and expected values purely by chance. We can compute the chi-square critical value with only the significance level and degrees of freedom. Let's do that. Degrees of freedom is k number of categories minus 1. We have 3 categories, therefore our degrees of freedom is 2. The chi-square critical and chi-square computed will both use the same formula, chi-square.inv.rt for right tail. The probability when we're computing chi-square critical is our significance level, and the degrees of freedom. The chi-square critical value is 5.991. Our computed value, again using the same formula of chi-square.inv.rt, will use the p-value and the degrees of freedom, and the chi-square value is 9.88, which is larger than our critical value, leading to the same outcome. We would reject the null hypothesis. In this test, we assumed equal frequencies. The test also works with unequal frequencies. In this example, a transportation department in a small city needs to understand traffic patterns before installing a new traffic light. The city engineer believes 50% of cars go straight at the intersection, 25% turn right, and 25% turn left. That will become our null hypothesis, that the proportion of cars going straight is 50%, and that left and right equals 25%. The alternative hypothesis is that these proportions are not correct. A sample of 200 vehicles was observed to determine actual vehicle turns, and that is shown here. Let's fill in the column for expected number of vehicles. We are using an unequal expected value now. So 50% times the total. Lock that cell and drag the cell down the column. And now we're ready to compute the chi-square p-value. enter our actual range and expected range. As you can see, our p-value is greater than our significance level. Let's go ahead for completeness sake and determine the chi-square critical and computed values. Degrees of freedom will be 3 categories minus 1, and we'll use the chi-square.inv.right-tailed function. The probability for the critical value is our significance level with 2 degrees of freedom for a value of 4.605. We expect this value will be smaller than our critical value, and it is. We would conclude that the city engineer is correct and that the proportion of those turning right and left is 25%, while the proportion going straight is 50%. In this video, we conducted goodness of fit tests on nominal scale data using the chi-square test and determined that the same test will work for equal and for unequal expected frequencies. This video will demonstrate how to perform a chi-square test for independence on a contingency table. In this data set, we have a contingency table showing the results of a sample of 950 males and females who were asked whether they believe the current government has increased or decreased the deficit, or whether they have no opinion. Our hypothesis is that gender and attitude toward the deficit are not related. The alternative hypothesis is that gender and attitude toward the deficit are related. We will conduct the test at a 5% level of significance. In this table at the top are the actual results. To run a chi-square test in Excel, we need both actual and expected results. I've copied the table below, and we need to first fill in the totals. Then we can use the totals to determine the expected value. Control-C, paste special to get the values in. Control-C and paste special to get the values in. Now I can calculate my interior values equals the total of columns times the total of rows divided by the grand total. I'm going to lock the grand total because I don't want it to move away from that cell. I only need to lock the row designator reference for column totals, which means locking the 9. I need to lock the row designator, which is E. Now I can drag this down. Let's drag this across, and then we'll drag these down. We'll take a quick look here. It's multiplying no opinions total by male total and dividing it by grand total. If I select all of the cells down at the bottom, you can see that the sum is 950. We've now filled in our expected values table, and we're ready to calculate the p-value for our computed chi-square value. We will use the formula equals chi-square dot test. The only 2 items needed inside the function are actual range, and we will select the interior values of our actual values table, and the expected range. We'll select again the interior values of this expected values table and hit enter. This is in scientific notation. Let me make it a number, and we'll set that to be 3 decimal places. The p-value here is the probability of finding a difference between these 2 tables as large or larger purely by chance. The small p-value, far less than our significance level of 0.05, indicates the unlikeliness of finding such a large difference if our null hypothesis were true. We therefore reject the null hypothesis and conclude that gender and attitude toward the deficit are related. Let's go ahead and compute the chi-square computed and critical values. We need the degrees of freedom for that. Degrees of freedom for a contingency table when we're doing a goodness of fit test is the number of rows minus 1 times the number of columns minus 1. So our degrees of freedom is 2. Chi-square computed, we'll use the chi-square dot inv.rt. The probability is the p-value we've computed, and the degrees of freedom goes in the second part of the function. And our chi-square computed is quite a large value. If it exceeds our chi-square critical, which of course we expect it will, then we will reject the null hypothesis. Equals chi-square dot inv.rt. we use the significance level, degrees of freedom, close parenthesis, and chi-square critical is 5.991. This video demonstrated how to conduct a chi-square test for goodness of fit for observed versus expected values in a contingency table. This video will demonstrate how to use a dataset to build a line graph and generate a trend equation based on the least squares method. This dataset shows the production numbers in thousands for a manufacturing plant. We want to use the least squares method to generate an equation to forecast future production. I'll select the production numbers, including the label, then click on Insert and Line Plot. To generate the trend line, I left-click on the line, right-click and choose Add Trend Line. I'm also going to insert the trend equation. Linear is selected by default, which is the one I want. Let's go ahead and make the trend line a bit easier to see. I'll change it to black and increase the width of the line. And this is my trend equation. Let's copy it into the tab. On the graph, I can also update the x-axis labels to show years. Left-click, right-click, and select Data, and then I will edit my label range. I do not select the year column header, and you can see on the graph already that it has been adjusted. If I had included my years in the graph at the beginning, I would have ended up with a line graph that had 2 lines in it, which is why I had to wait to add the years to the x-axis. What we want to see with a trend line is that we have some values above the line, some below, without a pattern of values above or below the line. And we would like all of our values to lie relatively close to the line. The less the data fit the line, the more error we will have in our forecast. What this equation tells us is that on average, year over year, production increased by 1,190.5 units. I'm going to put my equation values in these cells. I'm going to name the cells by clicking on the name box here and typing intercept, and then clicking on the slope and in the name box typing slope. When I click on the slope cell, you can see that the value for slope shows up in the formula bar, but the name of the cell shows up as slope in the name box, whereas if I click on this cell, the name box shows I3. The value of naming a cell is that you can use it in any equation in any part of your spreadsheet, in any tab you create, and it will refer back to this exact cell. You can only use a name one time in any one spreadsheet, so I can only use slope once here. Each spreadsheet gets its own data file for all of the names that have been created. On the ribbon, we go to Formulas, Name Manager. You can see that 2 cells have been named in this spreadsheet. Naming a cell has the advantage of locking that value when you use it in a formula, replacing the need to click the F4 button. Let me demonstrate by calculating predicted production for 2006 equals, and then I can start typing intercept, and it shows up in this drop-down. The little yellow tag means this is a named cell. I can double-click it or keep typing, and Excel would select the first choice from that drop-down. The rest of my trend equation is plus this value of year by count, which is the x value in my equation, times, and I can click on the slope cell, hit enter, and it enters the value of 4.5834. Now I can Control-C to copy that and Control-V into 2013. You can see that the value for the year 2006 is above my actual production, which we could also see by looking at the trend line on the graph. And the value for 2013 is below the actual value. The values are fairly close to the actual, but we do expect error in our forecast. This equation also allows us to forecast ahead. I can copy this formula into my 2016 box. I can predict that in 2016 I will produce about 16,500 units. I can also extend the trend line on my graph. If I left-click to select the trend line and then right-click it to format the trend line, here I have the ability to forecast forward and backward. So I'll forecast ahead 3 periods. As you can see, by extending the trend line, Excel automatically added those years in labels on the x-axis. In this video, I've demonstrated how to use the least squares method to forecast by building a line plot and generating the trend equation. This video will demonstrate how to check for autocorrelation in a regression model. We already have the regression output for this data set, which is evaluating the predictive ability of 2 independent variables, aptitude scores and union membership, on job performance. Assume that the values were collected over time in the order given in this list. We want to verify whether our residuals are correlated with one another over successive time periods. In other words, whether we have autocorrelation. Excel output the residuals for me. We'll first plot the residuals to see if we spot any patterns, and then we'll check for the strength of the relationship by calculating the Durbin-Watson statistic. To plot, I select the residuals, click Insert, and choose Scatter Plot with a line connecting each value. Notice that our x-axis crosses the y at 0. If we want our x-axis at the bottom of the plot, we select the values on the y-axis, right-click, and choose Format Axis. I'm going to change this from -60 to -50, and then on axis value, I'll change this to -50. And now the x-axis crosses the bottom of the chart. Looking at the graph, I don't see a pattern. We don't have a run of values above the 0 or below, nor is there a pronounced upward or downward trend or a curve. Based on this graph, I predict that my Durbin-Watson statistic will indicate a lack of autocorrelation. For autocorrelation, we will check at the 5% level of significance. Our null hypothesis is that there is no residual correlation, and our alternative hypothesis is that a positive residual correlation exists. That's a standard set of hypotheses when checking for autocorrelation. The formula for the Durbin-Watson statistic at first looks complicated. However, we already have one of the numbers in our regression output. It is the sum of squares residuals in the Anova table, this value here. That's also very easy to calculate with a formula in Excel. The formula is equals sum square, open parenthesis. Let's click on this F sub x button. Sum square returns the sum of the squares of the arguments. We're going to enter all of the values from the residual column here and click OK. And we get the same number as we have in the Anova output. The numerator is E sub t, which is current period residual, minus E sub t minus 1, which is prior period residual. Square the difference and sum it up all the way down the column. Let me show you how to calculate it using a couple of additional columns. We're going to call our residuals column E sub t, which is current period residuals. Next to it, I've got a column called E sub t minus 1, which will be the last period's residuals, and then my square the difference column. When I say E sub t minus 1, what we want to do is subtract current period minus the last period. In order to set up this column of E sub t minus 1, I simply take the first value in the residuals column and put it against the second value in the residuals column. I'll drag it down the column, and we've now filled in a lagged residual column. E sub t minus E sub t minus 1 squared, we take the difference between the residual and its lagged residual and square it, and I'll drag it down the column. Now I'll use my auto sum button to fill in the value of 8514. Now that you see how to calculate this by adding additional columns, let's look at the formula that Excel offers us. Equals sum xmy2 It calls for two arrays. The first array is going to be our residual E sub t value. The second will be E sub t minus 1. I'll start with my second observation and drag it down to the bottom of the column, which is the last observation I'm using for E sub t. My second array, I begin with the first value in the residuals column, and then I end with the next to last value, which you can confirm by looking at the E sub t minus 1 column. And notice the output is already showing up in the function argument box, 8514, which matches the value that we calculated using several additional columns in our spreadsheet. I click OK. With these values calculated, I can now calculate the Durbin-Watson statistic, which is the numerator divided by the denominator. I've already looked up the upper and lower critical values in a table, which is in the back of your statistics textbook. As predicted from the plot of residuals, I will fail to reject the null hypothesis and conclude my residuals lack correlation. This video has demonstrated how to plot residuals and check for the evidence of autocorrelation, and how to calculate the Durbin-Watson statistic using residuals to conduct a hypothesis test for residual correlation. In this video, we will deseasonalize a dataset, generate a trend equation, compute a deseasonalized number, and reseasonalize it. We have a 5-year data set of quarterly information about visitors to a national park. Plotting the data provides clear evidence of seasonality. We can see that peak volumes occur in summer and winter. I'll also add a trend equation to the graph. The trend equation shows evidence of a negative trend. The problem with using this trend equation is that the significant seasonality will create error in any forecast. If we can remove the effects of seasonality, we can improve our trend equation for a more accurate forecast. I've copied the trend equation here, and we can use it for comparison purposes with our deseasonalized trend equation later. Since our data are quarterly, we need a 4-quarter based moving average. Then we need to center that average. Our moving average will begin in the second quarter, equals average, and then I'll select the 4 values for that year, and I'll drag this down the column. If I go all the way to the bottom of the column, unfortunately, I run out of data, and I'll have empty cells in my forecast beginning in summer. Those values are deleted. Now it's time to center the forecast. I'll take the second and third values and average them, putting that output in the third quarter. Now I have a centered 1-year moving average, which I will drag down the column, and again I'll need to stop when I run out of data. Spring 2013 centered moving average uses the last 2 data points. Now that I have the centered moving average, I can compute my ratio to CMA. It's equal to the number of visitors divided by the centered moving average. I will drag that down the column until I run out of data in both columns. And next, I calculate my unadjusted seasonal index. In a moment, I'll explain why it's called unadjusted seasonal index. This computation is the average of all of my summers, the average of all of the falls, of the winters, and the springs, equals average. And then I'm going to hold down the control key and select all of the summers in my values. I've now created a seasonal index for summer. I'll drag this formula down and just do a quick check to make sure that I've captured the 4 springs in the ratio to CMA column. We call this an unadjusted seasonal index because if I select all of the data and look down at the bottom of the Excel spreadsheet, it shows that the sum is greater than 4. These numbers need to add to 4 because we are computing seasonal indexes on 4 quarters. There's an easy way to correct this slight difference from 4. I will take the value I expected it to add up to, which is 4, and divide it by the sum of my unadjusted indexes. and I get a correction factor which I can then multiply by my seasonal index, equals the summer unadjusted index times the correction factor. I'm going to lock that cell so that I can drag it down the column, but I'm only going to drag it to spring. I now have my 4 indexes, and as you can see at the bottom, they add to 4. I can then copy and paste these values into all of the other seasons, but I need to paste special because I don't want the formulas to copy down. And I now have adjusted seasonal indexes, which I can use to deseasonalize my visitor number. The formula is number of visitors divided by the adjusted seasonal index, and copy down the column. I now have a column of the deseasonalized values for the visitors to the park over the 5-year period of time. I'm going to plot this data on a line plot. I'll copy and paste this formula, and we can now compare it with the original trend equation. As you can see, our trend equation still has a negative slope. Since these numbers are thousands of visitors, we've shifted the slope from a loss of 316 visitors per quarter to a loss of 36 visitors per quarter. Consider the difference in the forecasted results. For fall 2013, which had an actual of 72, with our original trend equation, we would get a forecasted value of 97.078. Let's compare that. Our second trend equation gives us a value of 99.688. Re-seasonalize the result of trend equation 2 by multiplying that value by the seasonal index fall 2013 predicted result of 73,903 visitors. This video has demonstrated how to deseasonalize forecast data, generate a trend equation, use the equation to forecast, and then re-seasonalize the result. This video will demonstrate how to build a Pareto chart in Excel. Here we have a data set where residents of a nursing home participated in a survey, and the results of their dissatisfaction have been put into a frequency table. We can convert this to a Pareto chart, which will help to determine which factors are responsible for 80% of the complaints. This is a quick process in Excel. I will select both columns of data, go to Insert, Charts, All Charts, Histogram, and select the Pareto function. Click OK, and the chart is inserted. I have a bit of cleanup to do. I should add axis titles, and I should change the chart's title, but otherwise this is a completed Pareto chart, which has been sorted from highest frequency to lowest, and we can see at a glance that we are at 80% of all complaints with the first 3 causes. This video demonstrated how to convert a frequency chart into a Pareto chart using one of the histogram chart options in Excel.